All right. So what we want to focus on here, the first little bit of the physics unit, we talk a lot about energy and the different kinds of energy. All right. That's okay. I actually skipped the this introductory page here because it wasn't really necessary. Yeah. So guys, sorry, it won't look like this page. It'll look like this page with the voltapile. Okay. At the bottom, it'll look like that. Right? Because I actually skipped over the first. So what we want to look at here at the beginning of this unit is energy. Because when we get to the end of this unit, we'll also be going back to it. We need to introduce what energy is, what are the different kinds of energy, that kind of stuff. Then we'll talk a little bit about movement of objects, speed, displacement, velocity, stuff like that. And then back at the end, we start getting back into work energy theorem, conservation of energy. So energy is a big part of this unit. All right, so we start out with it and we'll finish with it as well. All right. Now, here's the problem with energy. The idea of energy people could handle. Being able to prove that it existed, okay, and quantify it was difficult because you can't see energy. All right? You can't capture it. It doesn't take up space. It's not like matter. All right? But people tried to make it like matter. They had all these ideas that energy was this fluid, this invisible fluid, incidentally, that went through things and could transfer to other things. But fluids are matter. They have to have mass. They have to take up space, and energy doesn't do that. So it was really difficult for early scientists to define it, okay, and show people what it was. They could show people the evidence of it. They could say, look, this happened. Something had to cause that. It's energy. And people are like, yeah, well, it could be magic too. Prove it. Okay, and that was what was sort of the stumbling block, okay, early on. Now, types of energy that we knew about, obviously we knew about the sun's energy, okay? It causes snow to melt in the spring. Okay? It's thermal energy, it's radiant energy, okay? We knew that it could do stuff. We could see the evidence of it on Earth. All right, in the same way that you can see the evidence of thermal energy coming from a fire, from a campfire. Okay? So the development of the concept of energy went hand in hand with our development of technology that used it. Right? And that tends to be the way things have gone for us as a society, okay, as a race. We actually figure out ways to use stuff before we fully understand it. All right? And again, that's the way things kind of went with energy. And as we developed things that worked, we actually furthered our understanding of these concepts. All right? So we've got, through observing the changes in these technologies, we got an idea of the concept of energy. Now, 1850s, so mid 19th century, we've got this idea that there is this thing called energy. It was difficult to describe because it was an abstract idea and not a material object. Again, when it's matter, you can touch it, you can feel it, it's obviously there, but energy isn't the same. Okay? Experimental evidence supported the theory that heat was another form of energy, and it could be converted into other forms. Okay? And that was the thing that really led to people being able to figure out what energy was being able to convert it from one form to another. All right? We knew that mechanical energy, like a falling object, okay, or a moving train, right, things like that, could be converted into other forms. Because can you hear a train coming, even if it doesn't blow the whistle? Yeah, sure you can, because its mechanical energy is always being used to do work against the friction on the track, and that produces sound, which is another form of energy. All right? We knew that one form of energy could be converted into another. Okay? Heat could be used to do all kinds of things. Okay? It could be used to boil water. Right? It could be, used to cook food. It could do all kinds of stuff. Right? And that was kind of where things really got going. So the first thing we have to do is look at what are the different kinds, or forms, I shouldn't say kinds, the different forms of energy. Right? There's two kinds of energy. The two kinds of energy are essentially, okay, I shouldn't say that. That's not really true either. We'll look at the different forms. I'll explain it better in a sec here. Okay, we'll look at the different forms. Chemical energy is probably the most important for us as a society. Everything in our society seems to run on chemical energy. Chemical energy is the energy that is stored in the bonds of chemical compounds, okay, in the bonds of molecules. All right. So the big thing here is that when we burn certain chemicals, the energy that is holding those chemicals together at a molecular level gets released. All right? If we're burning, let's say, propane, this is what propane looks like as a molecule. Okay, there's 3 carbons, and then there's a bunch of hydrogens around the outside, 8 of them. All right. When we burn propane, these bonds all get broken. Okay, when they get broken, the energy that was holding them together gets released, and it gets released in the form of heat. Okay, we know that after this reaction happens, because it's a reaction with oxygen, we get carbon dioxide and water. So we know that when we burn the propane, we break every single one of these bonds. How do we know that? Yeah, Drew? Okay, there's no more propane left, and also, look at the products. Yeah, it's a combustion reaction, but how do I know that I've combusted and broken every single bond that was there in propane? Right, the carbon and hydrogen are no longer connected. Okay, in none of the products are carbon and hydrogen together anymore. We've broken every single bond in there, and we've released all the energy that was stored in each of those bonds. Right? That is how chemical energy works. When you break those bonds, the energy gets released, and it gets released as thermal energy or heat. All right. So chemical energy is the potential energy, okay, stored in the chemical bonds of compounds. Same thing. The food you eat, okay, contains chemical energy. When you break that food down in your mitochondria, okay, when it gets turned into sugar and then your mitochondria break it down, the same thing is going on. All right. So chemical energy is a form of potential energy. All right. Now, the whole idea about this came from Antoine Lavoisier. He realized that when you burn stuff, not all things burned as hot as others. Okay? Wood could burn fairly hot, but not as hot as coal. Coal could burn way hotter than wood could. All right? Which, of course, was important because coal was the fuel of the Industrial Revolution. Okay? But when in discovering this, he was able to figure out that, well, if different things burn hotter, different things must have more energy in them because they have the ability to release more heat. Right? And that was kind of the development behind different types of fuels. Right? Enriching and refining fuels makes them burn hotter because they have more potential energy inside. All right? Propane is one of them. Okay? Methane we don't use very much because, well, it doesn't have a lot of bonds in it. Okay? What stuff do we burn in our cars? What's the active ingredient in gas? It's usually listed as a number on the side of the pump. There's sometimes ethanol in there. Octane. You ever seen the number on the gas pump? Regular is usually 87 octane, mid-grade's 89, premium's 91. Okay? It's essentially how much octane is in there. Well, octane is C8, H18. Okay? Does that have a lot more bonds than C3H8 does? Okay? More bonds, more energy. All right? Paraffin, the stuff that's candle wax, is like C22. Okay? It's got tons of stored energy. That's why a little candle can put off a lot of heat. All right? If you have a candle in a small space, it can warm that small space up quite a bit because paraffin releases a lot of energy. All right? Everyone follow me there? Okay, so that's kind of the science behind fuels. Because it's a solid, won't flow through the pipe, through the fuel line. Yeah. All right, electrical energy and magnetism. Obviously, electricity is important, and we understand that we can turn chemical energy into electrical energy. Not directly, but we can use chemical energy to heat water. Water can turn to steam. Steam can turn to turbine. Turbines can make electricity. Right? Every time we do that, we're converting one form of energy into another, into another, into another. All right? The more times, though, you have to convert the energy, the less efficient your process becomes. All right? And anytime you're burning something, that's an inefficient, conversion of energy. So electrical energy is the work done by moving charges, namely electrons. So when you're using electricity, electrons are flowing through whatever device you're using. Electrons can flow quite quickly. All right? The better a conductor is, the faster those electrons will move. Okay, so if, let's say, you're making toast in the morning, all right? You got the toaster on. As soon as you press the button down, electrons start flowing into the toaster. But When they get into the element, that's the part that glows red when you're making the toast, okay, the electrons are slowed down because that part of the wire doesn't allow electrons to pass through it very easily. Okay? It is a resistor, we call it. And as it goes through, the kinetic energy, how fast those electrons were moving, gets turned into what? Heat and some light, because they glow, obviously. All right? So there's some heat and there's some light. We're converting that electrical energy into something else. Okay? Everybody with me there? So we know that if electrons can move fast, they can do work. Anything that moves fast can do work as long as it slows down while it's doing that. Then it's transferring the energy. Done. Most of them, because most heat sources are incandescent, which means they glow because they're so hot. Okay, like incandescent light bulbs, the old kind with the filament inside. Okay, they get really hot because they're high resistance. Right. All right, so with the voltapile here, okay, the voltapile is actually one of the examples of turning chemical energy directly into electricity. We can do that, right? It's just generally we don't, right? Unless we're using batteries. Okay? If you're using alkaline batteries, rechargeable batteries, okay, anything like that, then you're using chemical energy being converted directly to electricity. Right? This is the great-great-great-granddaddy of the AAA. Right? Oh, it's big. Yeah, the voltapile was like probably about as big as this hole punch. All right, and it was like a AAA, maybe less than that, maybe like a hearing aid battery or a watch battery. Okay, what it has essentially is these plates that are made out of metal, and they've got moistened pieces of paper in between them, and because there's these metals have a different potential than the paper does, you can actually get a difference in potential between the top of the pile and the bottom of the pile. If there's a difference in potential, the electrons flow from one side to the other. That's why there's a positive end and a negative end to all batteries. Okay? We create a potential difference between the two ends, and the electrons flow from one end to the other as long as they're connected. Everybody follow me there? All right, and that's why usually when you have a battery-operated device, the batteries alternate which way they go, right? Because they're wired in that way. That way you've got positive connected to negative and so on, and you amplify that effect. Okay? All right, so this is, like we said, the original battery, okay, and that is, it was developed by this guy, Alessandro Volta. Okay, that's where the unit for current, volt, comes from. Okay. All right, so the study of current, electricity, and electrical energy began with him, okay, because he was kind of the guy who was able to prove that electrons can move, and I can turn chemical energy into electrical energy. Now, it didn't take long, once we were able to build circuits and things that could carry a current, for us to find out that electricity and magnetism are very closely related to each other. All right? How many people have noticed that if you turn on the microwave, your Wi-Fi signal usually goes out? Anybody ever notice that? Try it at home. Okay? Take out your iPad or your computer, okay, and try and download something while the microwave is running. It won't work. Okay? Why won't it work? Because your microwave produces a magnetic field that disrupts the transmission of the Wi-Fi signal. Okay? A magnetic field disrupts things. It's kind of like jamming, electronic jamming. Okay? It just produces this big field that interferes with all other types of magnetically produced signals. Yes, that's how electronic jamming works. Now, they don't just fire up every microwave in the place, but they have like a big generator, essentially, that just spews out signals and magnetic fields at all frequencies and essentially just makes everything static. Okay? All right, so Ørsted was the first person to realize that electrical energy could produce magnetic effects. Okay, and he did it completely by accident. He was just setting up a demonstration for some students, and he had this current-carrying wire, and he just happened to have a compass. Okay, well, he put the compass, set it on the table, and ran the wire over top, not thinking. And as soon as he turned the current on, the compass oriented and pointed along the wire. Okay, went from pointing straight north to pointing along the wire. As soon as he turned the current off, the compass went back to north again. Right? So what he realized is this electrical field produced a magnetic effect. Okay? This is why there's those people out there that believe they don't want to live underneath like power lines because they believe it makes this field that'll screw them up. Some people believe that. There's not really much to it. Okay, but it does produce a magnetic field. There is a magnetic field around all current carrying wires. That's why all of the wires in your house have shielding around them. If they didn't, they could produce magnetic fields that would interfere with the operation of other devices. Okay, everybody with me there? All right. So if you hold a magnet above iron filings, okay, if you've ever seen that, if you take a bar magnet like this, okay, the filings will kind of make this pattern around the bar magnet. I don't know if you guys ever saw that in elementary school. Probably. Okay, so all the filings will orient with the magnetic field of the magnet. Well, the same thing will happen for a current carrying wire. Okay, the arrow will point in the direction the current is flowing. Not always, no. This one's not circular either, right? Like it makes this kind of weird flower shape kind of a thing. All right. They generally take the shape of whatever's producing them. The Earth's magnetic field looks just like this too. Okay, North Pole and South Pole has the same kind of shape. All right, so Oersted's the guy who discovered electricity could produce magnetic effects. Faraday took that and ran with it. He said, well, if that's true, I'll bet you the opposite is true. I'll bet I can take a magnet and produce electric effects. And this is how like a gas-powered generator kind of works. Okay, a gas-powered generator essentially just moves a magnet up and down through a coil of wire. And what happens when you do that, if you make a coil of wire and then push a bar magnet through it, what happens is you push the electrons in the wire down the wire. And moving electrons are electricity. Okay, so moving this magnet through the wire disrupts the electrons. The electrons get pushed around by this magnet, and they flow through the voltmeter, and it shows that you have a current going. All right, if that magnet is going in and out all the time, it produces alternating current, AC. Okay. All right, so we got that's Oersted and Faraday. Okay, two pretty important guys there. Okay, so Oersted discovered an electric current in a wire could produce magnetic effects, and Faraday, okay, showed the reverse could happen. He moved a magnet through a coil of wire and showed that caused the electric current to flow. People were getting pretty excited about all this electricity stuff. So another guy named Seebeck decided, I'm going to show that you can turn heat directly into electricity. All right, which would be great because that would be a great way to generate electricity if we could make it work. Okay, it does work. It's just highly inefficient. Okay, you do not get a lot of electricity directly produced from heat, but you can get it to work in a device called a thermocouple. All right, but like I said, it's not very efficient. It's not used to generate electricity. So in this thermocouple, okay, essentially what he had was two different metals, iron and copper. Now, electricity or electric current flows through copper way easier than it does through iron. All right. What happened is when he started heating up this end, the particles of iron started to move. Okay, because we know that when things get hotter, they move faster, right? Well, that movement was transferred to the copper. Copper conducts that movement faster than iron, so electricity started to flow through the copper. Okay, and it produced a current, and when that happened, the compass needle went from pointing this way to being straight in line with the copper wire, or the copper metal there. Okay, and that showed that he's got an electric current flowing through there. He showed that heat could be directly converted into electricity. Again, it's not very efficient. Usually, the use for a thermocouple is as a circuit breaker. Okay, how many people have seen the big breaker box in their basement? Right? If you overload a circuit, it pops, right? And everything that's on that circuit goes dead until you go flick the switch again. Okay? Essentially what happens is as that circuit gets too much electricity going through it, okay, it gets hot enough that an electric current will be produced that will flip the switch. Okay? And it'll cause that circuit to go off and prevent it from overheating and starting a fire. All right? So it's kind of used in that way. Okay? They're sometimes also used as switches, okay, to turn stuff on and off. All right, so that was Seebeck. Okay, Seebeck, he did the first thermoelectric converter, okay, which we also call a thermocouple. Okay, because it couples two different metals together, thermocouple. All right, nuclear and solar energy. Okay, Henri Becquerel was really an important guy in terms of discovering the nature of electromagnetic radiation. Right? For the longest time, people looked at the sun and they went, geez, that's bright. And then they said, it's bright because it's a fire. There's this big fire in the sky. Okay? Because that's what it looks like. And really, when you look at pictures of the sun, it looks like it's a big fire. But it's not a chemical fire. Okay? That's what people didn't realize. Right? A lot of people thought the sun is a big fire like you would have a campfire. It can't be. If that was the case, the entire mass of the sun would have only lasted 5,000 years before it would have all burned. All right? The sun is not a chemical fire. It is a nuclear fire. All right? It is a nuclear fire produced by one of the two types of nuclear reactions. The two types of nuclear reactions are fission and fusion. Okay? In nuclear fission, okay? So, sorry, I should talk about what nuclear energy is first. Nuclear energy is the potential energy stored in the nucleus of an atom. Okay? When an atom stays together, there's all this energy that holds the protons and neutrons and electrons together. Okay? When you split an atom, that energy is released. Okay? That process is fission. Okay? When the nucleus of an atom is split, okay, you get fission. When the nuclei of two atoms combine, you get fusion, and energy is released. Fusion is highly energetic, way more energetic than fission is. All right? And that's what goes on in the core of the sun. All right? The sun is fusion powered. The sun is so massive, okay? It's made almost entirely of hydrogen, and it is so massive that its own mass causes so much gravitational pull that in the center of the sun, there's so much force that it can force hydrogen atoms together and turn them into helium in the process of nuclear fusion. All right? That process doesn't happen, okay, under accidental conditions. There is just so much huge gravitational force. The sun is essentially crushing itself. It is so massive. Okay? And our sun is small on the scale of stars. All right? But it is so massive that it is causing the hydrogen atoms to force themselves together. Everybody with me there? Yes, Dom? They get bigger because as they exhaust their fuel, they turn their fuel into other types of matter, right? So eventually when the sun starts running out of hydrogen, it'll start burning helium. Well, that happens at a different temperature than the fusion of hydrogen. And so as a result, the sun swells. Okay, and as it starts to swell, there's all kinds of forces that come into play, electron degeneracy force and all this kind of stuff that just causes the sun to undergo massive changes very quickly, and then the sun essentially dies. Okay, our sun will not go supernova because it isn't big enough. It'll simply cool off and die. Okay, oh, you don't have to worry about it. It's a few billion years away. Yeah, not a problem for us to ponder. If it swells, and it probably will expand out to the radius of the Earth, yeah. Yeah. Yes. Yeah. It should swell that big. Yeah. After that, though, it doesn't have the mass to fuse the heavier elements. As it tries to fuse helium, that's when it'll get really big. Once it's fused all the helium, it's going to have heavier things like carbon and stuff like that, and it doesn't have the mass to force those together into even heavier elements, and that's when the fusion will stop, and it'll shrink back down and become like a white dwarf. Okay. All right, so like we said here, originally the scientists thought that the source of sun was chemical energy. However, they soon realized it would only take about 5,000 years before the mass of the sun would have been burned up. Okay, so solar energy results from hydrogen nuclear fusion, okay, and the release of nuclear energy. The nuclear energy we use here on Earth is all fission-based. All right, the splitting of atoms. All right, fusion, like we said, is much more energetic and it's much harder to contain. All right, so it's difficult to build reactors, right, that will endure that kind of energy release. All right. Now, motion and energy. Anytime you've got something moving, it's got energy. It's got mechanical energy. Okay, and mechanical energy is mostly what we're going to deal with in this unit. Mechanical energy is the energy of objects because of either their position or their movement. Okay, potential and kinetic energies. All right. Now, this is Newton's cradle. Okay, you guys probably all seen these things before, right? You pull it and it goes click, 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 back and forth. This nearly got Newton beheaded, believe it or not. Okay, this did not make him a very popular person because Newton lived in the time when people believed in witches. And as soon as he did this, people are like, you're a witch. You made that ball on the other end go up. You're a witch. Okay, and he had to really kind of backpedal, okay, and kind of get himself out of trouble here by coming up with the concept of mechanical energy and this living force, he called it. He didn't call it energy. He called it this vis-a-vis, or living force, okay, that caused things to do that. That way it wasn't magic, and he wasn't going to get burned at the stake or drowned or whatever they did to witches. Okay, so he kind of had this idea here, but there were no theories to explain why that happened. He just kind of said, well, there's this living force here, and it, when I put my living force into the ball by lifting it, that living force can do other stuff. And people then said, okay, you're not a witch. All right. Now, a little bit later, okay, a guy named Gottfried Leibniz, okay, reasoned that whatever caused the ball to move was some kind of force that could be transmitted through all the others. Because if you've ever watched this, the center ones don't move. Okay, the energy is passed through them to the one on the outside. Since there's nothing to hold it there, it flies up on the other side. All right, so he came up with this vis viva, okay, living force idea, okay, but we'll use energy because that's essentially what we use now. So there's different kinds of there's different parts to mechanical energy. Anything that has to do with movement is kinetic energy. All right, so wind, okay, water, falling object, whatever, can do work because they're moving. If they run into something, they will slow down, and whatever they hit, they'll do work on. All right, they'll transfer energy to it. If you've ever played pool, okay, you know that this works, right? If you hit the cue ball at another ball, okay, the cue ball hits that ball, the cue ball slows down, the other ball speeds up, okay? Energy is transferred. We call that work. Work is a transfer of energy. All right? An object raised above the Earth's surface has the potential to do work, okay? And as a result has gravitational potential energy. And these two things are what explain how Newton's cradle works. When you take the end ball and raise it away from the others, you do work. Okay? You transfer energy to the ball because you have to give it energy when you lift it up, right? Anytime you lift something, are you doing work? Yeah, well, when you lift that little ball away from the others, you do work. Work is a transfer of energy. So now that little ball has gravitational potential energy. Because if you let it go, what's it going to do? Right, it's going to fall. Okay, go down toward the others. When it does that, it's turning that gravitational potential energy into kinetic. When it strikes the other ball, it does work on that ball. That ball hits the next one, does work on it, and so on till it hits the last one. That one moves up. Okay, all the energy gets transferred through and over to the other side. Done. You mean like out to the side? It typically doesn't work. Just because it doesn't swing properly that way. I mean, theoretically, yes, it should go off at exactly that angle, but it's going through three other balls. If it comes in at an angle, then the next ball isn't directly in opposition to it, and that second ball might slide out to the side, so you'll get this kind of weird wishy-washy motion of it. Okay. All right, so Leibniz, he wasn't right about energy being a force, okay, but he was right about this idea of the mechanical part of it. Okay, if you add the potential energy and the kinetic energy of an object, you have calculated its mechanical energy. Okay, mechanical energy is the sum of all the kinetic and all the potential energy that an object has. All right, heat and energy. People knew these two things went together because they could see it all the time. In order to generate heat, you had to do something. You either had to set something on fire, or you had to, slide two things past each other really quickly, right? Something like that. You had to do work, you had to expend energy, and usually heat was produced as a byproduct. Everyone with me there? Like, it's as simple as if you rub your hands together, it gets hot. All right, your hands get hot when you rub them together. Why? Well, because you're doing work and there's friction there, and that friction will generate heat. Okay, so the Greeks obviously realized that. Okay, we have the atomists that we talked about back in the chemistry unit. Okay, they thought this heat must be the movement of little particles. But again, they weren't widely accepted, okay, until much later on. Now, Joseph Black, okay, he observed that when a cold object was placed in a cup of hot water and then removed, the cold object was hotter after. Wow. Okay, we probably all know that, right? If you take a cold spoon and you're stirring your coffee, when you take it out, the spoon's hot. Why? Transfer of energy. Conduction. Yeah, okay? Those are both. Conduction is a transfer of energy. Here's what he discovered. Energy only flows one way. Energy always flows from the high energy object to the low energy object. From hot to cold. Never the other way. Right? You can never make coldness transfer to something else. Okay? Now you're probably thinking, I think you're wrong, Coderre. When I put ice cubes in my drink, I make my drink colder. I transfer coldness to my drink. See, Coderre, you don't know what you're talking about. But I do. Okay? Here's why I do. You're not transferring coldness to the drink. The ice cubes are absorbing the heat. The heat is going from your drink to the ice cubes. Okay? They are the colder object. Energy always flows from hot to cold. Your drink is hotter compared to the ice cubes. Ice cubes take a lot of energy to melt. That energy comes from your drink. That's why your drink gets colder. Okay? You can't transfer coldness. You can only transfer heat. All right? Everybody with me there? All right? Eventually the ice cubes melt, right? And eventually then your drink will start warming up. Why? Because the surroundings are warmer than your drink, and they will transfer energy to the drink because it always goes from hot to cold. So Black, Joseph Black, was very important in that he discovered this idea here, thermodynamics, the direction of movement of energy. Okay, thermodynamics is the transfers or conversions of energy. All right, so he explained. Now, unfortunately, he wasn't right about everything. He was the invisible fluid guy. Okay, right? He had this idea that if something had lots of energy, it had lots of this caloric fluid that could flow from one thing to another. Well, that's not the case. Okay, but it is how energy works. Energy does flow from one thing to another. It's just not a material. Okay. You can't create or destroy energy either, but it can be transferred and converted to other forms that are less evident. Okay, so if I look at like a roller coaster, okay, on the top of the first hill where it's not moving very fast. Okay, it has, let's say up here, let's say 4,000 joules of mechanical energy. Right? Well, when it comes down to here, it's going a lot faster. Agreed? Okay, but let's say that down here it only has 3,000 joules of mechanical energy. Where'd the other energy go? Friction, yeah. Okay, it was used to do work against what we call non-conservative forces like friction, air resistance, stuff like that. Okay, what evidence do we have that that energy is still around? You can hear the roller coaster. Not the people screaming on it, okay? Just the roller coaster. You can hear it rolling along the track. That's evidence that some of this 4,000 joules got turned into sound energy. Some of it got turned into heat, okay? Things like that. I'm not destroying the energy. I'm just not turning it all back into kinetic. Some of it's turned into other forms. Yeah? Yes. It just wouldn't be very efficient. Okay? That's how our hearing works. We use the fact that sound energy can be converted into other forms in order to hear. When the sound energy strikes our eardrum, it makes our eardrum vibrate back and forth, right? So that's mechanical energy there, and that's used to send signals to our brain. All right, so Black was trying to perfect his caloric theory. Okay, other scientists were looking at this atomic motion idea again, and that's kind of where the atomists kind of started getting a little more credit. Okay, we call the transfer of thermal energy from a hot object to a cold object heat. Heat isn't a form of energy. Okay, we kind of get taught that along the way, but it's not really true. Heat isn't a form of energy. Heat is a transfer of energy. Okay, it's a transfer of thermal energy, right? We feel heat, right? If you stand in front of a campfire, do you feel? Right. Because it's transferring thermal energy to you. You are colder than the fire, right? We don't feel heat. We feel the thermal energy coming to us from the transfer of thermal energy. That's heat. Okay, the transfer of thermal energy. So we want to make sure we keep those. We often confuse heat with thermal energy. Heat is a transfer of thermal energy. Okay, in the same way that work is a transfer of mechanical energy. All right, heat and mechanical energy. This guy here, Benjamin Thompson, who for some unknown reason changed his name to Count Rumford. Okay, I don't know why, but he did. Okay, he was the Minister of War in Bavaria during a time when Bavaria was apparently at war, and they built lots of cannons because that's what you use to blow stuff up. Okay, so his job was to supervise the construction of these cannons, and what he discovered was that as the workers he had were boring out these big blobs of copper. Essentially, that's what a cannon is. You take this big solid hunk of copper, and then you take a big, it looks like an ice auger, okay, or a post hole auger, if you've ever seen those, okay, and people just turn this thing, which looks like a big drill, okay, until they bore a big hole into this thing, and then you have a cannon, because a cannon is really just a tube, okay, so you're boring this thing out to make a tube. He discovered that as they bored the metal, it got really, really hot. In fact, so hot that the workers would put a tea kettle full of water on top of the cannon, and while they worked, it would get so hot they could boil the water and make tea. So he kind of invented the coffee break. All right? Because by the time they had done enough work to boil the tea, they could take a break. And they could have a cup of tea. All right? Where's the energy coming from for all that heat? Friction. Okay? Well, it's not so much that friction is the energy, it's the work being done against friction. The energy to boil that water is coming from the people turning the drill. Their food that they ate is being turned into mechanical energy, the movement of their muscles. They're turning this drill, which is scraping past the copper of this cannon. And as it does that, it's encountering a lot of friction. Okay? All of that mechanical energy, their movement, gets turned into heat. Okay? And that heat transfers through the cannon to the surroundings. Okay? It just so happens that the tea kettle is also in contact with it, so a lot of it transferred to the tea kettle. Right? People had to be very careful when making cannons. You didn't want to, oh, sweet, the tea is ready. You lean against the cannon and then you burn your hand. Okay? So you had to be very careful around those things. The shavings, I'm not sure. I would imagine they would melt it down again because there'd be quite a bit of it, right? It's not destroyed. It's just you'd have, if you melted it down, you'd have another blob of copper, right? You could make more. Yeah. All right. So his big thing was he discovered you could convert mechanical energy into heat. Okay, that's what he showed. All right, and that was an important discovery. So where does it say that here? Right? He noticed the supply of heat was endless as long as the workers continued boring the hole. As soon as the workers stop, the cannon starts cooling off. Right? Because the source of energy is no longer there. Okay? As soon as they stop working, the cannon would start cooling off. All right? So he showed that heat and mechanical energy were related. Okay? That one could be converted into another. All right. Now, again, we had this. We had Thomas Young here. Okay, he linked this mechanical energy to this idea of kinetic and potential energy. All right, he's the one who said, well, mechanical energy is the movement or position of objects, so we're going to say that mechanical energy is actually both of these, which we know now, of course, to be true. Okay, he also thought mechanical energy was related to the work a system can do, and that is also true. If we go back to our roller coaster example up here, okay, in the perfect physical world, if there was no friction, the amount of mechanical energy here, 4,000 joules, is the same as it is down here. If there are no forces that can steal the energy, no forces to work against, the energy at the top and the energy at the bottom would always be the same. And that would be how much work that system could do. All right? Now, how much work do you suppose you need to put in order to get the roller coaster up here where it has 4,000 joules of energy? A lot, yeah. How much exactly? 4,000 joules. Okay? If you want that thing to have 4,000 joules of mechanical energy, you have to do 4,000 joules worth of work. Right? That's the only way it can get that energy. Oh, absolutely, yeah. Friction is essential. I mean, friction always works against you, but it also without it, you wouldn't be able to walk. All right? I mean, think about it. When you walk, you push the world that way, and the world pushes you this way. Okay? Without friction, you can't push backwards. You'd slip, just like you do on really, really slippery ice. Right? We all walk differently in the winter, right? When you get onto a patch of ice, you pick up your foot and set it down, right? You don't push backwards. You step on, you lean over onto that foot, get all your weight over that foot, and set the other one down so that you don't slip and fall. If you try and do this on a sheet of ice, he'll slip and fall because there's no friction there, and he'll just flip over. Okay? Don't make me throw something at you. Stay awake. What's that? Well, yeah, if you got sticky boots, yeah. What about it? If you slide across the ice, what? Oh, yeah, but if we're saying if the whole world was frictionless, you'd really be in trouble, right? Because you could never make that run at it and slide across. How would you ever get running if there was no friction, right? I mean, you could maybe go like this and hope that the wind would blow you, right? And then you could get going, but then you'd have, how do you steer, right? Without friction, you couldn't steer either. Yeah, and you'd never stop. Yeah, that would be the other problem. Yes, that's why in space you always want to stay tethered to something, because if you run out of the little propellant in your maneuvering jets in your suit, you'll float away for all eternity. Yeah, and that would suck. All right, so mechanical energy there, we talked about that. Okay, last thing here. The most important guy when it comes to mechanical energy, energy of any kind, is Joule, because that's who got the unit for energy named after him. Okay, when you do important stuff, you get the unit named after you. Newtons are the units for force. He discovered all kinds of things about force. The unit for force is the Newton. All right, so we got first Sadi Carnot, okay, who was a French engineer, and he tried to transform heat into mechanical energy, which you can do, but it's just not a very efficient transformation. Heat is kind of the lowest form of energy. You can turn heat into other forms, but it doesn't work very well. But almost all other forms of energy can readily be turned into heat because it's the lowest form. Okay, everybody got me there? All right. So essentially what he discovered is that you can transform heat into mechanical energy, but it could only occur when you had hot to cold. Okay, so this is, we'll talk about this probably tomorrow, but this is how heat pumps, or not heat pumps, heat engines work. A jet engine is a heat engine. All right, it harnesses the fact that energy flows from hot to cold. All right, and if you can get something between the hot and the cold, as the energy flows through it, it'll affect that object and it'll do work on it. Okay, and that's how a jet engine works. You've got blades, fan blades essentially, between the hot area of the engine and the surroundings, which are cold. As that heat flows through the blades, okay, it brings air with it, and the air turns the blades, and you've got a jet engine. Okay, so kind of stuff like that. Now, Joule showed unequivocally with two very simple experiments that mechanical energy and heat, okay, are interchangeable. All right. So what he did is he took this this apparatus first, okay, this apparatus with the two hanging masses, and he had this kind of jar, and inside the jar were these blades with holes in them, and he had a thermometer in there, and he was showing, okay, that kinetic energy could be turned into heat. So essentially, as these things fell and the blades started turning, the air inside this jar warmed up because there was something moving past the air, and that could change the temperature, okay, within that within the tube. All right. Now, this one showed the potential energy. These masses here have potential energy, and when they fall, that potential energy gets turned into kinetic. Okay, warmed up this. This one was even more simple. It showed pretty much the same thing. If I take this big block, okay, and I pull it up to here and then I let it go, it'll swing down and smash into this stationary block. All right. When it's up here, it has potential energy, but when I let it go, the potential energy turns into kinetic energy because it speeds up. Okay, and when it smashes into the stationary block, the temperature of the stationary block goes up. All the kinetic energy this thing had turned into heat and sound because you'd hear them smack together. All right, the same thing happens when you hammer a nail into wood. All right, in fact, you don't even have to have a nail. Just go home today, get a piece of wood and a hammer, and just bang on the same spot on the piece of wood with the hammer, and put your thumb where you were hitting. It'll be hot, right? Because your mechanical energy, okay, from swinging the hammer and having it hit that piece of wood has to turn into other forms. Because when your hammer stops, all that kinetic energy is gone. It's got to turn into other forms. Those other forms are sound and heat and the deformation of the wood. Yes. Okay, again, friction, okay, kinetic energy doing work. Yeah. All right, so that was what Joule showed. Joule showed, okay, that heat and mechanical energy could be interconverted, okay, from one to the other. All right, so Joule, like we said, pretty important guy because he quantitatively proved that that can work. All right, you have on your in your notes here these questions. All right, I'm going to want a few of these answered. I'm going to circle which ones here. Okay. I want you to do number 2. Okay, I want you to tell me what each of these people did. Okay, and I want you to tell me what the practical applications of those things are today. I want you to tell me the difference between fission and fusion. Okay, I want you to tell me about that one. Okay, number 9, number 10. Okay, number 12, because that's telling me what type of energy is involved. And 13 and 14. These are just kind of quick answers. There's a few of these that will require full sentences, and then most of them will just require something quick. All right, so those are the ones I want you to do. So 2, 3, 4, 6, 9, 10, okay, 12, 13, and 14. All right, you got the rest of the class to work on those. That, I would say, is probably quiz material next week. All right, remember you have your unit exam on Monday. Okay, you need to be studying for that tonight and over the weekend, okay, so that you're ready for that. All right, and then, yeah, that's it. You've handed in all your stuff now. We've got all of these. Yes, you can. Is that what you were going to ask?